All right, today we will start Chapter 4. And so Chapter 4 regards the application of derivatives. So it's a very important chapter. A lot of engineering and economics theory and other natural and social sciences theory depend on the results that we'll explore in this particular chapter. So today we'll start section 4.1. So we'll call this Lecture 4, Part 1. Okay, and this will be an introduction to applications of differentiation. Okay, now, so we'll start off with a discussion of what maximum and minimum values of a function are, and we've kind of worked on this through the course of the semester. If you recall the first project we did, I asked you to identify maximum and minimal points on the graph of a function, and the typical way we have up until this time was to identify maximum and minimum points as points of transition from where either the curve was decreasing to increasing or increasing to decreasing. So a point of transition happened there. So we're going to develop a facility for identifying more precisely these properties of functions. And once we know this, then we can start interpreting the results. So maximum and minimal points are essential for the solution to what are called optimization problems. And these problems we're required to find the optimal best way of doing something. So for example, what is the shape of a can that minimizes manufacturing costs? Okay, so should it be a cylinder, should it be a sphere, should it be a box, and so forth. Okay, you have material costs, you have enclosure costs. So you want a can that minimizes cost but perhaps maximizes a volume would be a consideration. What is the maximum acceleration of a space shuttle or a space rocket so that you can overcome the Earth's gravity? And we've already dealt with some other examples, such as, we have, from your algebra experience, you may have encountered problems where you're trying to maximize the enclosure of a rectangular enclosure, and you eventually modeled the enclosure as the form of a parabola, and then you sought to find the vertex of a parabola which either maximized or minimized perhaps some physical constraint. And so vertices of parabolas are either maximize or minimize certain things. And so we've already dealt with that from an algebraic sense. But now we're going to really open up and use calculus to solve a wider range of problems. Okay, so yeah. Okay, so before we proceed with these optimization problems, we can explain what we mean by maximum and minimum values of a function. Right? So here we have a very important definition. A function f has an absolute maximum or global maximum at, say, x equals c if the output at c is greater than any other output for the function for all inputs in the domain. Okay, the inputs being x. Okay, all right. So f of c is called the maximal value of f on the domain. And then we have conversely, we have the absolute minimum of a function occurs at x equals c if the output of the function at c is less than or equal to the output of the function for all x in the domain. So it's the point that's the lowest on the graph of all the points on the graph. All right, so we'll see, and that's one of the techniques we'll develop in this chapter, is to identify precisely where these values occur. Okay, so here we have a hypothetical function shown in red, and for all intents and purposes, we can consider the domain to be where the function is shown. All right, so any place outside of the interval on the x-axis where you don't see content, that will not be the domain. So, so in this case, what the note is saying is that there's an absolute maximum at D, okay, and that's evidenced by the fact that at this particular point, there are no other points below it, above it, that is. And then there's an absolute minimum at A, which happens to be an endpoint of the function. Okay, all right. And so now if we look at this point, Okay, it's a minimum point in a neighborhood of C on this interval, but it's not the absolute minimal point. Likewise, this point right here at E, it's a minimal point only if you're near E on either side of E. But then again, it's not the absolute minimum. And likewise, this point right here at B, it's a maximal point. It's a local maximum in the neighborhood of B, but again, it's not the overarching maximal point. Okay, so there's a dichotomy of classifications of points. I wouldn't worry too much about it at this level, but just be mindful of this. There may be a web-assigned question or two where you explore these concepts. So yeah, so like we said, if we consider only values of x near b, in this case in the neighborhood of b, A to C, yeah. So in this case, what the note is saying, if you only consider this interval A to C, then f of b is the largest of those. And so this is a local maximum, like we said. Okay, so local maximums, local minimums. So yeah, here's the technical note for local minimum. Okay, as we just discussed. What do we have here in slide 15? Okay, all right, so here's the definition of a local minimum as contrasted with the global minimum, or excuse me, local maximum is contrasted with the global maximum. So a function has a local maximum at x equals c if f of c is greater than f of x when x is near c. And technically speaking, this language is somewhat imprecise. Instead of x near c, I'm going to often say x is in a neighborhood of C. Okay, and we know what a neighborhood is, right? It's just a collection of points, a small collection of points or a subset of the x-axis that contains C. Okay, so that's another way mathematicians use these words more so than near. Okay, so the neighborhood is an open interval. So that means, if you recall, an open interval on the x-axis, you use parenthetical marks as opposed to brackets. Okay, so that's what we mean by neighborhood. And then minimum, so if the output of the function is less than f of x when x is in the neighborhood of C, right? So we'll use that terminology as well. Okay. All right, so let's see what else we have. So consider the function f of x, which equals to cosine x. It takes on local and absolute maximal values at 1 infinitely many times. Okay, since we know that the cosine of 2n pi is equal to 1 for any integer n, and we know that the range of the cosine function is between -1 and 1 for all x. So look at the graph of the cosine function. Recall what its graph is. So the cosine function goes like this, okay? So it never goes above 1 and it never goes below -1, right? And so you have all of these integral multiples of 2 pi, the output will be 1. So, and then -1, of course, is the minimal value. So in this case, the local minimum is the same as the global minimum, and the local maximum is the same as the global maximum for the cosine function. And there are infinitely many such, right? Okay. Okay, so what else? What other kinds of functions? Okay, so consider y equals f of y equals x squared. And then we know that the x squared function is always greater than or equal to 0. And so therefore the origin is an absolute and local minimum of f. So, and you can deduce that just by knowing the graph, which we all do by now. of y equals x squared. So the vertex is at the origin, and all the points on the parabola y equals x squared are above the origin. Okay, so that's conceptually what's going on. So next. All right, so yeah, here's y equals x squared again. Yeah, so like I just said, there's no highest point on the parabola. Okay. All right, so you can see we have a global minimum at the origin, and it turns out that this global minimum right here also happens to be in a neighborhood on the x-axis. Okay, and so that makes it also a local minimum for this neighborhood. Okay. All right. All right, so now consider the graph f of x is equal to x cubed. Now, this function has neither an absolute maximum nor an absolute minimum. So it has no local extreme values, right? And one of the reasons why, as we alluded to in earlier lectures, is because y equals x cubed is a constantly increasing function. Okay, there's never a point of transition from increasing to decreasing. Okay, you never see any decreasing intervals along this graph, and because there's no transition, there can't be a local minimum nor a local maximum. However, we did discuss earlier, I believe it was chapter 3, that the origin is an inflection point, because we notice to the left of 0, the function is concave down, and to the right of 0, the function is concave up. Okay, so it exhibits, y equals x cubed exhibits two types of concavity, and they transition at the origin. But for now, we just need to know that there's no local or absolute max, nor local or absolute min. Okay. What else can we discuss? Okay, and so here we have a graph of a polynomial, 3x to the fourth minus 16x cubed plus 18x squared, on a domain of -1 to 4 inclusive. All right, so we can identify a global max, a global min, a local max, and a local minimum. Okay, so let's see what kind of arrangements we can make with this particular function. Okay, so f of 1 right here, which equals to 5, is a local maximum. Okay, because you can see in the neighborhood of 1, it is the largest point. It is the largest point on the graph. See, we consider, say, this neighborhood of 1 right here. Whereas if we look at f of -1, this point stands out above all the other points on the graph. Okay, so that's a global maximum. But pay particular attention to this note right here. The absolute maximum is not a local maximum because it occurs at an endpoint. All right, so if the absolute max occurs at an endpoint, it cannot be considered a local maximum, because typically what we look for in local maximums are being points of transition from increasing to decreasing. Okay, and this is not a point of transition from increasing to decreasing. Okay, it's an endpoint. And in endpoints, you can't have transitions. All right, do you see that? See? We're increasing and decreasing. And so when you have that point of transition, it has to be a local maximum. Although it can be, as in the case of the cosine function, a global maximum. But at endpoints, it can be a global maximum or an absolute maximum, but it can't be local because there's no transition. Okay, so that's the nuance of the terminology. Let's see what else we can do. Talking furthermore about this graph, the origin is a local minimum, okay, because it's a point of transition from decreasing to increasing, and f of 3 right here is a local and an absolute minimum for the graph. Okay, now at the endpoint, at this endpoint at x equals 4, it's neither local nor an absolute maximum. It can't be local because it's an endpoint, and it can't be an absolute max because it's not as high up as -137 on the graph. All right, so that's the structure. Those are the structures. Yeah, so some functions have extreme values, whereas others don't, like in the case of y equals x cubed. Okay, extreme values being the absolute max and the absolute min. All right, so now we have a theorem which attempts to classify these extreme points. So we have what's called the extreme value theorem, and this is a very important theorem. Okay, so extreme value theorem I will often refer to as EVT. Okay, so we'll call this EVT because at times we'll use the extreme value theorem in conjunction with the intermediate value theorem, which I call IVT. Okay, so we have those concepts. So EVT and IVT. So it goes like this. If we have a continuous function on a closed interval, then the function attains an absolute maximum value at x equals c and an absolute minimum value at x equals d at some numbers c and d on the closed interval. So this is quite profound. Basically, well, I think the next slides will show you, but if you have a continuous function on a closed interval on the x-axis, then that function will attain at least one maximal value and one minimal value on that closed interval. So that's how you kind of surmise what it's all about. So let's see, we'll probably give a picture, I'm sure. This guy tends to really get verbose. Yeah, so here we go, some examples. So consider the first frame of the graph in the first frame. Here you have the function being continuous on the closed interval a to b, and you can identify c. The output of the function at c is a global or a local. Yeah, global or local, it doesn't matter because you're on a domain. The domain is only a to b. A local maximum at x equals c and a local minimum at d. So again, the continuity asserts that you'll have these, at least one of each. Okay, and then here's a function. I'm looking at the second frame now. In this case, the global minimum occurs at the endpoint b, and then c occurs in the interior of the interval. And then in the third frame, you'll see an example of a function that looks kind of sinusoidal, and it has two maximals at C1 and C2 and a global min at D. Okay, and again, it's continuous on a closed interval, and the endpoints can participate in the characterization of a global max or a global min for the domain restricted to the closed interval. Okay, and of course, if the function's domain is the entire x-axis and you're only considering the interval a to b, then we'll dispense with the word global and we'll use the word local. Right. Okay, so what next? So we won't prove it. It involves a lot of topology. And so some counterexamples or exceptions to the extreme value theorem, to EVT. In this case, the first frame, this graph does not have continuity on the interval 0 to 2, so you cannot apply EVT here. And in the second frame, x equals 2 is a vertical asymptote for the graph, and so it's impossible to obtain the coordinates of an absolute maximum for this function on this interval. Nor can you obtain a global minimum, because at x equals 0 there's a hole, right? So this function is not continuous on a closed interval. And by continuous we mean that the function does have to exist at the endpoints. Okay, and let's see here. And the reason why it fails here is because we have a jump discontinuity, and we can never, and it has a hole at the highest visual of the graph, and so we can never obtain precisely the coordinates of a maximal point because of the presence of the hole and the density of the real numbers. Okay, all right. So what's next with EVT? Okay, so here's the explanation. So it's defined on the closed interval. This function is defined on a closed interval, but it has no maximal value. Let's see. And so they say the range is 0 to 3. I would say 0 to 2. no, the range, the output. Okay, yeah. The range is 0 to 3, and notice that 3 is not included. And the function takes on values arbitrarily close to 3, but never actually attains the value 3. And that's why we don't have an output where the ordinate of the output is the greatest of all the outputs because of the density of real numbers. We always get infinitely close to 3, but no matter what your ordinate is at x equals 1, or as x approaches 1, no matter what your ordinate is, I can always beat your ordinate by just adding a fraction more. And that's called the density of real numbers. Okay. Yeah, and then of course f is not continuous. But even though EVT stipulates that a function has to be continuous, the converse of the EVT is not necessarily true. A discontinuous function could have maximal and minimal values on a closed interval, okay? But you just can't use EVT for discontinuous functions, right? Okay, so G, okay, it's continuous on 0 to 2, but it has neither a maximal nor a minimal value. And so because the range, you can see the range is from 1 to infinity, the function takes on arbitrarily large values, and it doesn't contradict EVT because the interval 0 to 2, for which the function is defined on, okay? The function is defined on an open interval, okay? In this case, it's defined on an open interval. The endpoints are not included, and the fact that it's only defined on an open interval means that it violates EVT because EVT requires that the interval be closed, right? So you see why it's open? Because it's not defined, the function is not defined at the endpoints of the interval 0 to 2. There's no closed interval for which this function is defined. None. Okay? All right, so what's next? Okay. Okay, so the theorem doesn't prescribe how we can find the extreme values on an interval, on a closed interval, okay? So let's see how maybe we can develop a facility for doing so. Now, this is why are we doing this? Okay, because this is the beginnings of the hunt for local minimums, local maximums, absolute minimums, absolute maximums on the entire x-axis. So right now we're just taking kind of what's considered a baby step. We're just looking for extreme values of a function on a closed interval of the x-axis. And then as we develop this facility, we'll dispense with having closed intervals on the x-axis and we'll extend it to the entire x-axis. So let's just see if we can solve the problem on a small part of the x-axis first, and then we'll develop the facility for solving this problem on the entire x-axis. All right, so here we have a graph of a hypothetical function with a local maximum at C and a local minimum at D. And now, if we look at the tangential lines drawn at the local max and the local min, the tangent lines are horizontal and they have slope of 0. And of course, we've already worked on this problem substantially in the previous chapters. Notice that the maximum is a transition from an increasing to a decreasing function, and the minimum is a transition from a decreasing to an increasing function, okay? And at the point of transition, you're neither increasing nor decreasing. So if you're neither increasing nor decreasing, then the slope of the tangent line at that particular point will be 0. And so hence, lines with 0 slope are horizontal lines, okay? So this is a very important concept here, okay? Okay, so we know that the derivative is the slope of the tangent line. So f prime of c is equal to 0, f prime of d is equal to 0. All right, so, and then we have, for differentiable functions, we have what's called Fermat's theorem. Okay, so if a function f has a local maximum or a local minimum at x equals c, and if the derivative at c exists, then the derivative at that point x equals c is equal to 0. A very profound theorem. Okay, so if you recall your first project where you were hunting for local mins and local maximums, this would be the technique, one technique you could use to evaluate your conclusions. Simply take the derivative of that function and plug in your choice for the abscissa of the local min or local max, and if the derivative evaluates to 0, then you've found it. Okay? Right, so suppose that f has a local max at x equals c. Then according to the notion of a local max, the output at c must be greater than the output at any x when x is in the neighborhood of c. Right? So here we go using kind of an epsilon delta or difference quotient technique. So if h is close to 0, with h being positive or negative, then the output at c is always going to be greater than or equal to the output at c plus or minus some delta. Okay? Right, so remember, c plus h defines a neighborhood. C plus h, c minus h defines a neighborhood about c on the x-axis. So what's going on here is essentially this. Here's your x-axis. Okay, suppose h were greater than 0. So this would be c minus h. Here would be c, and then this would be c plus h, like so. All right, so you would have something like that. Okay, and so f of c would be something like that. Okay, and so we transform this inequality. We subtract f of c from both sides, and we have this inequality right here. Okay, so remember this inequality when I go to the next slide. Okay. So we take the inequality from the first preceding slide and divide both sides by a positive number. So if h is greater than 0 and h is not 0, okay, and h is sufficiently small, we'll have this result. So we have the difference quotient, right? So if f of c is a max, and we can construct this inequality where the difference quotient is less than 0. Okay. Now remember that f of c is considered to be a local max. All right. Okay. And so we take the limits. Remember, we take the limits of the difference quotient as h approaches 0. And so we take the limits of both sides of the inequality. And so we have the limit as h approaches 0 from numbers bigger than 0 would equal to 0. Okay. Because the limit of a constant is equal to the constant itself. Okay, and so if we look at the preceding slide, remember we started out here, and now we just take the limits of both sides. Okay, so it follows. All right, so what's next? Okay, since we know that the derivative, we stipulated that the derivative at x equals c exists, we have the derivative at c. And this is the definition of the derivative, right? The limit as h approaches 0 of the difference quotient. And that's the same as h approaching 0 from numbers bigger than 0 of the difference quotient. All right, so the limit as h approaches 0 is the same as the right limit. Okay, and so we have that the derivative of the function of x equals c must be less than or equal to 0. So why can it be less than 0? Because where did the inequality come from? Okay, so the inequality came from here, right here. Let me see if I can select. Okay, well, we actually can do this. If we go back here, what's not immediately obvious in this slide is that we actually did this. We took the limit as h approaches 0 of both sides of the inequality. Okay, and so that's where it became less than 0. Okay, so let's go back to that slide. I forgot what number it was on. It's not that one, this one. This one. So this one. Yeah. Okay. Okay. So remember, the reason why we have an inequality here, and so this isn't quite true. We should technically have perhaps something like this, because we know that f of c plus h is less than f of c. All right, so maybe I should write that down. It's not very intuitive here. F of c plus h is less than f of c because we consider f of c to be a local maximal. And so therefore, this quantity should be less than 0 because h is positive. Okay. All right. So for f prime of c, we have f prime of c is less than or equal to 0. Okay. And remember, f of c. Keep in mind that f of c is a local maximal. All right. So pressing forward. Now, if h were less than 0, then of course the direction of the inequality would be reversed because we're dividing by a negative number. Remember, when you divide by negative numbers in an inequality chain, it changes the direction of the sign. So now, so h in this case is less than 0. And so why do we want to make h less than 0? Well, because in the previous slide, we were to the right of f of c. Okay, so in the previous slide we had, all right, so here's our c value. And we were coming at c from this direction. Okay, so here is c plus h. Okay, and so we were doing this in the previous slide. Now we're coming at c from this direction. Okay, so here is c plus h. Okay, so h is less than 0, so we come at it from here. Okay, and so in this case, since h is less than 0, f of c plus h is f of c plus h, of course, is less than f of c. So we have a negative over a negative, and these two quantities are not 0, and so it stands to reason that this rational function will be greater than 0. Okay, so that's what's going on here. All right. Okay, so moving on. All right, and then of course we take the limits, and in this case we're taking the left-hand limit, and f of c plus h is less than f of c. H in this case will be less than 0. Okay, so we approach 0 from numbers smaller than 0. H will approach 0 from numbers smaller than 0, and then we get we have the result that the derivative will be greater than 0. Okay, as we approach it, as we approach f of c from the left. So what we've basically just done is we've approached x equals c as a transition point from an increasing function right here, increasing to decreasing. It's the same concept we've been talking about all along. Okay. All right. So we've shown that f prime of c is greater than or equal to 0, and also f prime of c is less than or equal to 0. So this would essentially be the squeeze theorem. Okay. And since both inequalities must be true,